In this video I will show you how high-res bitmaps, sprites, music are put together to a game, and I will give you some information on the source code, on the game loop, on interrupts and such things. As you can see, I have already started the compiler. Let's load Tempus. F1 load source, so here it is. I will not cover every line of the code, but I will highlight the most important functions. And of course, you can leave a message if you have any specific questions on the code. First of all, as you might already know, TCC is not a language like BASIC. BASIC is highly sophisticated, and TCC only offers a very small subset of instructions. It's a compiler, but it is not a basic compiler. TCC is built around an inline assembler that makes it very easy to exchange variables and labels between the more readable TCC code and assembler code on the other hand. And it is perhaps a bit more structured and a bit more comfortable than plain assembler. And when you look at the code, it doesn't look like assembler. Whenever a functionality is not available with an instruction in TCC, then I would use the inline assembler instead. So usually I would think a point-and-click graphic adventure game would need much assembler inside. But the demo game is controlled completely with TCC commands and library routine calls. There is not even one additional assembler instruction in the complete source file, and this is somehow amazing. Let's have a look at the code. The first thing we can notice is that the starting point is set to 5000, as I've mentioned in one of the previous videos. TCC searches for this directive somewhere in the first line, but after the file name. The first line is reserved for these two informations and is not compiled. I declare all variables in one section between var def and, as you can see here, var end. This is not necessary, but I like it this way. This also acts as a string table, so most strings that the game uses are declared once and in this section. Maybe one thing about this preset directive. This means that the specified value is written to the memory locations when the variable is created, and there is no need for a runtime function to assign the value to the memory locations, and this simply saves memory. Let's turn to the setup of the game. This is, from my point of view, relatively simple to the useful libraries. For example, SoundLoad loads the splitted export files to the locations that we wrote down during the export. For example, this was 0 for the first file, and it was 2303 for the second file. The 6 at the third parameter is the length of the file name, and the file name is a string. The label starts with the memory location at which this string begins, and this label location is passed to SoundLoad. Let's go up again and look if we can find the label file 1. So yeah, here it is. Here's we see file 1 points to the string wrong 1, and file 2 points to wrong 2. The string itself is also called file 1 and file 2. This is not a problem for TCC. Variables can have same names as labels or commands, and nothing can happen. So let's go back to the setup. The next routine that I want to discuss is sound reset. The settings for the sits are made with sound reset, and the song pointer is set to the start of the first song with set pos. The first song always starts at byte 100 because the settings for the 4 sits require 25 bytes for each sit, and these are also the first 100 bytes in the first export file. Sound play sets the player to play. Sound is output from the moment the interrupt redirection to the wedge is switched on. Next, the sprites that we have edited previously are read in. Here, also like in the sound load function, the string is passed to the routine using a label. F-sprite points to animation bin, which is the file that we have saved in the monitor. IO load, this is this routine, works a little bit differently to sound load and requires an address to which the file is loaded to. This is in this case 2000 or decimal 8192. The copying from bank 0 to bank 4 is done with the routine IO DMA. Started and target addresses are passed as parameters. So IO DMA copies 2688 bytes from bank 0 address 8192 to bank 4 address 32768. Okay. So, and next, the memory area is overwritten with the first bitmap. The label BMP points to a string that holds, I think, let's look. Here we have the label BMP, and it points to a string setab.temp. And this is loaded to 2000 or decimal 8192 and overwrites the data where the sprite has been loaded to before. Next is these addresses are addresses of the palette register. A total of 3 sprites are displayed simultaneously. These are the sprite for the upper body, the sprite for the legs, and the sprite for the cursor. All 3 sprites get the same color palette, and I do this with the sprite copy function. We obviously don't copy sprites here, but I can use the routine for everything where I want to copy byte for byte. And that's what I want here, because DMA doesn't work for the IO registers. The addresses used here are the, as I told before, the palette registers. The next important function is IO split screen. This function performs the basic setting for the raster line interrupt, and it switches to text mode at raster line 203, and it switches back to high res mode at raster line 251. And here the following function calls switch on the 3 sprites. So for the upper body, for the legs, and for the cursor. And you can see here that the sprites for the upper body and for the legs are expanded to X and also Y, but all 3 bytes are full color sprites. Yes, so The next poke that I want to show you enables two byte sprite pointers, which is very cool. So I have a second byte that sets in which bank and in which of the four 16 kilobyte segments the sprite is stored. The location inside the 16 kilobyte segment is controlled by the lower byte of the sprite pointer, and this is done as it was done in the Commodore 64 with 64 byte slots, so a maximum of 256 different 64 byte slots make up these 16 kilobyte segment. I like to have this, the sprite pointers at a very common location after the screen memory, and this is usually around decimal 4080. So I had set the high byte to 15 and the low byte to 240, and so the sprite pointers begin at 4080 decimal. Now let's look at the pointers themselves. The higher bytes, which are 4081 and 4083 and 4085, are all set to 18. This means the third 16 kilobyte segment in bank 4 at 48000. So we have as I am explaining also in the comment, we have 4 times the bank, which is 16, and an offset of 2 for the third 16 kilobyte segment, and so this is 18. The lower bytes are very important. This is the 4080 and the 4082 and the 4084 for the 3 sprites respectively, because they actually control the sprites, since the higher bytes never change. The first sprite is set to 0, and the second sprite that I have defined in the animation source file is 3, and the third sprite is 6, and the fourth sprite is 9, and so on. Always 3 more, because each sprite needs 3 64 byte slots. So when the character is walking, actually I simply change the value of the poke address at 4082, and this does the complete job, because the address at 4082 is the address of the legs sprite, and this does the complete job. So this is quite self-explanatory, but the next interesting part is the so-called wedge. This is where the interrupt are redirected whenever they occur, and in TCC the complete wedge is the area between the command IRQ begin and IRQ end. So inside the wedge, the sound and the input-output library take over most parts of the jobs. For me left, it is just calling the standard routines, as for example, IO raster IRQ, which does all the raster line switching according to the information that was given with the init split screen routine. As you can remember, this was the raster line to switch to text mode, and the raster line to switch back to high-res bitmap mode. So for me, it's just left to call the routine. The library does the complete rest. Or another of these wonderful functions is sound next. Sound next simply handles the next event, but I do not need to take care if there is a next event. This is all done inside the library. Maybe let's see a little closer to the cursor fx subroutine and do the walking subroutine and just move the code to this location. So I have the do the cursor fx subroutine here. The cursor effect is done with the color of the cursor. And the color palette entry has a value for the red and for the green and for the blue part of the color. This is controlled with the addresses 53,549 and 53,805 and 54,061. And all three registers are set to the same value, so the color is always a certain amount of gray and always between white and black, and this does the complete effect. The second routine, cursor fx, increments or decrements this value and changes the direction if the value reaches 0 or 15. That's all. Do the walking does the walking animation and sets the correct sprites. The character walks if its position is other than the target coordinate. As you can see here, for example, if the position is smaller than the target coordinate, then the character is walking to the right. So let's see the go right subroutine. Depending on the value I walk, which can be 1 or 2 or 3, the one relevant sprite address, which is at decimal 4082, gets the values 27 or 30 or 33, which is the correct address of the corresponding sprite for the legs. The upper body is set to 9, as it is done here, and this is the walk right upper body, and this is controlled with the address 4080. So now if the character reaches the target position as it is queried here, then it jumps to the no-go subroutine, which is here, and this simply sets the upper body sprite to 0 and the leg sprite to 36, and this does set the standing sprite. So next topic is the game loop, and I will just move up in the code to the game loop, which is done here. So the game loop is, as you can see, not very long. It simply has a delay first, and then the joystick status is queried, and depending on the status, one of the routines are called. So, for example, if it is 119, then it jumps to the RT label, which is here. It's the first one, and this simply increments the cursor X position, and then there is a check on the right border. So if the cursor X position exceeds the right border, then it is set to the right border, and so it goes back, and it goes to fin loop, and this just sets the sprite to the sprite 2 is the cursor sprite to these coordinates, and it goes back to the game loop. But what's more interesting event is the fire button. So if the status of the joystick is 111, the program jumps to label fire. So let's go to the label fire. So this is here. Handling fire button is a lot to do. So here's the label fire. Let's assume the player clicks on examine, then the is in routine gives back a return value of 1, and this is queried here, and so the program jumps to the label click examine, which is done here. So this sets the mode to 2 and gives back, goes back to mod 1, which is here, and this simply clears the command, the second half of the command line, and goes to the end fire loop, which is here, updating of the command. This is not so very interesting, and this simply goes back to the game loop. Now when the player so the player has clicked on examine, and what we can see here is that they simply changed the mode to 2. So now the player clicks somewhere in the level, then of course none of this is in calls would give back a return value of 1, and so it comes, the mode is 2, not 7, so it comes to this switch level, and depending on the level, a certain subroutine is called. For example, let's assume we have the level 1, then the program jumps to the do level 1 subroutine, and let's see what is done there. So so here it is, do level 1, and this is not a very long routine. So you can see every clickable element in the level is checked on the coordinates of the element with another routine, and this is the routine do. And we will have a closer look on this routine, since I think it's the most important routine for all the level stuff in the game. So let's go up to the do routine, and this is here. So first of all, it checks if the element is near or is in, and if it's not in, then it returns. It simply returns, and it gives back a 0. So there is nothing to do with this element. But if it's in, first it sets the return value to 1, and then it checks if it's near, because certain elements can only be examined, for example, or turned on if the player is close to the element. So And then, and this is more interesting, is that this routine is on the one hand not very long, but it is very efficient because it does all the linking between the element coordinates and possible items in the element which come with the parameters 7 and 8. And the mode, on the other hand, and as we can remember, the mode that is which action word has been selected before, and it hands over to certain processing routines. So depending on the mode and depending if it's near or not, it gives over to some certain special task routines. For example, a special walk task. So level 4 is the Dr. Tempus house outside, and the object 7 is the tree trunk, and the object 8 is the tree top. And if it has the action walk to, which is mode 1, then the do routine would hand over in mode 1 to special walk task, which is here. And the target coordinate would be 179 if it's set, if the object is the treetop, and this leads to that the character instantly starts to climb up the tree, since the interrupt just checks if the tx or the ty variable are not the same as the position of the character, and if this is the case, then the corresponding sprites for the walk animation and so on are done within the interrupt routine, and this is the only thing that triggers it. So it's not quite long and not very complex, but it does a wonderful job together with the interrupt. So, for example, the special turn on task. As we can see, if the level is 5, which is the attic in Dr. Tempus' house, and object is 5, which is the time machine control unit, then a certain kind of clue information is given depending which time it is, before or after the player solved the game whole puzzle. And for the one case it goes to the clue 3, and for the other case it gives over to clue 5. Yeah. For example, what we can see here is the special examine task, which checks on the status of some objects and either gives a clue information or simply does nothing. And all of these is controlled with the do routine. The other functions in the listing are more or less explanatory, and they are not too complex. So if you would want to add another level, then you would make a new do level routine, such as the do level 1 routine. And you would have to call this do level routine from the fire subroutine. So here you would say case 9 do level 9, for example, and that's it. The game logic itself doesn't have to be changed that much, even if you would want to create a complete new adventure. From my point of view, this completes it. If you have any ideas and want to know where to start, please leave a comment or write to me on the forum 64. This completes my introduction on how I made the demographic adventure game. I hope you got a lot of new information together with the other videos, and bye bye.